All
Action.
right, action time, Xavier. Thank you very much for joining us today and giving us to talk about your this really cool resin you have created for us. The floor is yours. Thank you.
Thank you very much. Thanks a lot, Erin, for inviting me today. What I'd like to introduce to you today is the work we've been doing in the past, let's say, 3 to 4 years. We started in 2017, this work. And the initial idea was that we recognized that there was a need in the field for something that would be conductive. And this was strongly pushed by at the time. So a lot of this project is relying on his push in this direction. So what I'd like to present to you is more or less how we got to create the R221 and where we are at the moment, but it's not a completely finished project. And those of you that are using the resin already know that there are a few things that are still missing or still under development. So I'll go straight to the point. I won't detail why we do CLEM, because if you're here today, it means that you're aware of what is CLEM. I will not explain what type of CLEM is available, because again, if you're here, it means that you're already an expert and you feel confident in the idea. What I will focus is the in-resin fluorescence and volume correlative microscopy, which is really the point of this resin. But there are hundreds of ways of doing correlative microscopy, and this is not the purpose of this presentation. So basically, there are many workflows. Dynamic CLEM, I will not go into the details, but in the in-resin fluorescence volume correlative microscopy, there are a few steps which are quite critical, and I'll try to present them before presenting the results, because I think this is the background required for the understanding of how we design this resin. So there's the fixation first step, which is essential, and it's actually, in our case, we use vitrification. I'll go back into that question just afterwards. And then the embedding, freeze substitution, which is also a critical step, and both steps are important. And obviously the applications we could find are 2D CLEM, that's one thing, but also 3D volume CLEM, which is quite important. And I will focus mostly on this 2D, on this volume correlative microscopy. So in correlative microscopy, there are a few bottlenecks, and I'm sure you're all well aware of them, but the critical steps are in multimodal sample preparation. If we want to do correlative light and electron microscopy, the purpose of the resin today, we need to have something which will be compatible both with light microscopy and electron microscopy. And if we do dynamic CLEM, so we look at something alive and then fix it, somewhat we separate those two steps of light and electron microscopy by the fixation step. But if we want to do in-resin fluorescence microscopy, then the protocol must be compatible both with the light microscopy and the electron microscopy, and this is where it becomes a major challenge. And so, of course, this is related to the imaging techniques as well. Whether you want to do light microscopy, electron microscopy, atomic force microscopy will influence the way you prepare your sample. And so a few years ago now, there was a paper that presented in a very attractive way a preservation of the fluorescence after high pressure freezing and embedding in lava acryl. This paper gave rise to the in-resin fluorescence correlative microscopies, and we've seen a lot of these applications now, and I think this is a very beautiful technique. But then kind of a bit before, but it was still under the radar for many, was also the development of volume electron microscopy by serial block phase imaging, which is a bit different from electron tomography and serial section in tomography. And so the interest of the project that I'm going to present today was to be able to combine those two techniques as efficiently as possible. And so before going into that, I'd like to redefine exactly what we're looking for. What is vitrification? What causes crystallization and then therefore dehydration? This is a very naive presentation of the work, but I think this is quite self-explaining. I'll try to have the laser pointer. Laser pointer. Yeah. Yes. So basically, we have here an illustration of what could be done with vitrification by high pressure freezing and vitreous sectioning. This work was done by me a few years ago during my PhD, at the beginning of my PhD. And the way we understand vitreous water is basically the water is immobilized in a structure which is similar to when it's liquid. So basically, it's not crystallizing. And when the water starts to crystallize, one of the big question is basically the ice crystals starts to grow and pushes away the material which is inside. The second point is the crystal tends to like being as pure as possible, so it will extract the water from the molecules surrounding it so that it can grow. And why it does that, it dehydrates progressively the proteins which are around, which give us this kind of gradient of quality of images, where we have here the semovis, considered as being the best imaging we could do. And then we have a very, I would call it perfect plastic ultrastructure. So basically the structure looks very close to what we're expecting from the semovis, and things are looking smooth and round, and the gradient is rather homogeneous. So basically we have a homogeneous staining. And then we start to see the ice damages, basically where the segregation starts to become stronger. And then we have ice nucleation, which are excluding the proteins, and therefore you have a very dense protein around a white core. And then you start to have more crispy aspect of the images. And that's the beginning of bad crystallization, bad vitrification. And then, of course, this is the obvious case when you have a very disastrous freezing, and then you have ice bombs everywhere, and you have ice crystals and dry matter all around. This looks disastrous. And unfortunately, we've all seen that once if we've done some high pressure freezing or vitrification. Another naive way to present that is basically we have a phase segregation. So this is obviously not the same case, but that's quite illustrative. When you have orange juice that segregates in your fridge, and then suddenly you start to have like the phase which is segregated from the liquid. That's just an illustration. Of course, this is not the same mechanism beneath. And this is the same drawings illustrating the same thing. Basically, you extract at each step of crystallization, you extract some water molecules to grow your ice crystals all around, and you have your dry matter inside. This is a naive presentation, but I think this makes the point. And so a second part of this is this fluorescence, vitrification and crystallization causes some dehydration of the material. And so a view of it is the fluorescence in the sample, when you vitrify it, will depend on the state of crystallization you have. To some extent, and I have no clue, this is an abstract view of it, but I expect that to some extent, a minor crystallization or very tiny crystals of ice will not necessarily affect the fluorescence in your sample. And then the more the crystals grow, the more it affects the structure of the GFP. Let's take this as an example. And so then suddenly you'll start to have a decrease in the fluorescence, while the ice damages and ice nucleation grows. In the middle, we have some kind of autofluorescence. Maybe this is actually not true, and basically it's following exactly the same line as the massive ice damage curve I'm presenting here. I don't know about that, but I know that at some point when we vitrify the material, we start to have autofluorescence emanating from the ice crystals. What causes that? How does it work? I have no clue, but this is something we observe in cryo stages. And so this approach gave rise to very attractive technologies of cryo-like microscopy, and I will not go into that details, but I wanted to put that into context because this is important in the fluorescence preservation that we will look into afterwards. And so there are a lot of very beautiful papers about that. Here are the references. I don't think I have all of them in the Dropbox, but you can find them fairly easily. Now I'll try to go into the freeze substitution steps. So basically, after high pressure freezing your sample or vitrifying it by plunging, what we are going to do is to extract the water, the solvent, so the water solvent, and replace it by another solvent like acetone, alcohol, and then replace this acetone and replace it by a resin. We use this acetone or ethanol step because the resin itself will not remove the water on its own, or at least not the ones we're using in our labs. And so what is interesting is that the polarity of the solvent will influence the type of free substitution and the contrast we will gain. There was a very beautiful paper about that that came out in 2007 that showed that preserving some fluorescent, some water in the free sub cocktail will preserve the contrast. And one way to understand that is that basically the full dehydration of your proteins might collapse the fluorescence and might make the proteins dehydrating so much that then the stain have hard time to go into the proteins to contrast them. That's an interpretation. Again, I'm not a pure chemist, so this is a visualization of the idea. But then basically, if you keep some water, you will keep somehow the structure, the very core structure of the proteins, including the fluorescent proteins. And then you can replace it by a resin and you will embed your whole sample. And so basically you don't dehydrate it too much. So basically the resin and the stain can start to penetrate the protein and give some color in your free substitution. And so then we go into we go from the water molecules, which is rather thin, to a solvent. Here is the acetone and here is the ethanol. We see that the structure is quite different. The acetone in the end has 3 carbons, so it's a bit bigger than the ethanol, but then it has the same type of polarity as water has. So it's very polar molecule compared to ethanol, which is slightly less polar. And then we replace that by HM20, and this is one of the key questions we have here. And basically we try to embed the sample into a resin. So that's the concept I just mentioned. Basically, we have the water molecule supporting the proteins, and then you dehydrate it using acetone, but not fully. So basically, the very small part of the molecules will remain maintained by the water. And while you add this acetone, you come in it with some uranyl acetate or some contrasting agent, heavy metal salt, together with fixatives. UA is a kind of a fixative, but you can also add glutaraldehyde or osmiums and other molecules. And again, there are many ways of doing the fixation. And then you replace this acetone by the resin, and basically, hopefully, you'll have deposited some stain in the different areas of the molecules of the proteins you're interested in, and therefore you will start to gain some contrast. You increase the density here locally so that the electrons will not go through too easily, and then you will gain some contrast in your TEM. It's not only the heavy metal salt that gave some contrast. The protein themselves also have a density, and they will slow down some of the electrons. So basically, depending on your electron setup, electron microscope setup, you will have some contrast even without contrasting agent, but it will be very mild. And so, based on this HM20 work, there has been 3 papers that I believe are setting up the path to us on how we do in-resin fluorescence microscopy. The first one was by Susan Nixon, then we had Wanda Kukulski, who made a marvelous work on even combining this fluorescence on section with very high precision localization, and she pushed that to temporal resolution with the yeast work she did. And then Chris explored also all the applications of this preservation and combining it with quick free substitution as well, and showed that we can have an optimal preservation of the fluorescence at some stage. And so the problem is that when we do this free substitution, we come up with fixatives and with some stain. And these guys, they come and they just fix the proteins together, and somehow they prevent the molecules to resonate. And that's one of the key points, is the GFP has to be able to vibrate, to be able to fluoresce. And so if you put too much fixatives, or if you put a resin that tends to attach to the groups, like amine groups in the epoxy resin of the molecules, then you will start to prevent this vibration. And then the molecule, the GFP, will not vibrate anymore. And so there is some kind of an optimal situation where basically the adjunction of any fixatives or stain will start to decrease the fluorescence. But then this is what gains you also a significant contrast in TN. So we could see it as there is an optimum in resin fluorescence where we have a very low amount of UA and a preserved fluorescence. But the problem is this balance is kind of not optimal for both. So basically you will not have a very good fluorescence and you will not have a very good contrast. And this is especially problematic for volume electron microscopy, where currently one of the major view of it is that we need to have a very high amount of contrasting agent to evacuate the charges in scanning electron microscopy approaches. So that's one thing. And the second thing is also the size of the molecules we're using. Osmium or uranyl acetate are very large molecules. And so they also tend to be quite bulky into the protein so that they quickly prevent any vibrations and things like that. In addition to the chemical reaction they do when they attach the molecules. So what we wanted to do was to be able to reduce as much as we could the stain and fixatives and to preserve the fluorescence and have some as much as possible fluorescence to do in resin fluorescence. And then, of course, we wanted to evacuate the charges. And so the first idea, as I mentioned at the beginning of this talk, came from Roger Veff, who said, like, look, I've tested this resin that came up in 1986 that was marvelous, gave amazing results, very high contrast, and I didn't have to put any heavy metal salt in the free substitution cocktail. Could you do it again? He asked me that because at ClioCapsel, we're quite familiar with polymers. This is one of the specialty of the company. And back then we were working in a polymer lab. So basically our company was hosted in a polymer lab. And so basically that was the main question. Could you reproduce this resin? So that was the first idea. But then when you read the paper and when you discuss with him and other chemists around, is basically the production of this resin is quite problematic. It could be explosive and it's not very stable a long time. So while putting an explosive compound in the lab is not always the easiest material. And this is something that as a company, you don't want to do. Because you sell it to a guy who does not do the right thing, and then suddenly you have a problem because, well, whatever happens. So as a company, you don't want to sell TNT to anyone, or you're no longer a biotech company. So what we decided was to go and start from a blank page, not trying to take what was existing, but trying to rethink the whole process from the very beginning. And for that, we worked with a chemist, a polymer chemist. And so the prerequisite we had were to have something that after embedding would become electroconductive. How does it work? How would it work? We had no clue. And that actually that was the aim, but we had no ideas of the path. Obviously, we wanted to have a very high contrast, and we could afford having some traces of contrasting agent, but that was not the only idea. If we need to have heavy metal salt, we use it, but that's an option. It should allow some water during free substitution, so it should have some hydrophilicity to some extent, because the papers before demonstrated that it increases the contrast, and basically the idea of the protein collapse and everything remained valid for this study. Obviously, it should preserve the fluorescence properties. That was the idea. And so we wanted to avoid the cross-linking. So any resin reacting like the epoxy was kind of out of the scope, because epoxy resin react with the amine groups of the molecules, and therefore it blocks the fluorescence. This is why EPON is not ideal for preserving fluorescence. It's not ideal. It does not mean it does not allow it. There are some papers around that. Or you would need to remove the EPON after you do the sectioning, which is done. It has been published and everything. I've never gone into these protocols personally. The first idea was it should remain liquid at -30 degrees, because we wanted to take inspiration from the Lovicryl that is to us the gold standard, and I've used it personally mostly. So I like the Lovicryl for its ease of use. And so having something liquid at -30 degrees was something interesting. It should polymerize under UV because, well, warming up the resin while you want to keep it at -30 degrees is kind of counterproductive. And I wanted to have a resin that could be stored in a chemical cabinet, not polymerizing because it's stored at 20 degrees. So the UV is convenient because it prevents having a early degradation of the resin. Obviously, it should remain transparent to visible light after polymerization, or at least the range of GFP, RFP. And it should allow sectioning by microtomy, or obviously ion milling after polymerization. And I'll come back to that microtomy step later on in this presentation. So I know that some lab did some tests to load existing resin with conductive agent. So here I showed you some carbon nanotubes or some carbon black or some silver flakes and things like that. That was one of the idea. And one of the first things we realized is that even if you take carbon so-called nanotube, indeed they're nano, but if you look at this image and if you look at the scale bar here, you would realize that this carbon nanotube will never, ever go through the plasma membrane of a cell, simply because that's way too big. And so it cannot diffuse inside the cell. And since it cannot diffuse inside the cell, what would be the best case scenario would be that these carbon nanotubes will drain the electrons outside of the cell, but not inside, where we have the material of interest. So we did not go into this carbon nanotube approach to start with. Carbon black is an option. We've heard that some lab did some trials with this and they were not so happy with the results, or at least we have not seen the results. I mean, I have not seen the results myself, so I cannot evaluate how much it was efficient. So basically the idea is the following, and the electrons will be gliding over the carbon nanotubes, but since the carbon nanotube cannot enter through the plasma membrane, well, basically the electrons that will be inside will remain sticking and they will somehow charge. And that's what we see in the scanning electron microscopy process. So basically the idea would be that your cell would remain charged inside while it will discharge outside. That's an option, but that's not sufficient to what we were looking for. And so what we decided was to try to start from the idea of the Lovicryl and try to create a resin that would eventually be charged with ions like silver ions or zinc ions, like it was proposed in this tin resin. So basically trying to charge the resin with some silver or some metals inside the composition to try to become somehow conductive. And so this was one of the ideas. And we've then decided to test a large variety of resins. So basically with our polymer chemist, we created a huge amount of resins. And I will not go into the details of that because this is part of the R&D. But basically what we were doing is high pressure freezing batches of cells, free substituting them together in the same in the same machine, removing. Andreas is,
Everything okay, Xavier?
Yeah, no, I see Andreas talking and the microphone is not off.
But he may be just chatting in the background. Okay. It's okay.
I thought he was interacting. Please excuse me. So the idea was to do this comparison to be able to evaluate the behavior of the resin in comparison with HM20. So each time we were doing a free sub run, we had one batch of whatever resin it is and one batch of HM20, and then sectioning it all and then looking at the different aspects. So what we were looking into was the contrast in the TEM, and I'm talking about the TEM because where I was doing this research at the Institut Curie, we did not have an SEM. So since we had locally a very good TEM, I just used that. We wanted to have the general intensity of the images because that's an indication of whether you have good contrast or not, a good evacuation of charges. How do we do the focus and astigmatism in SEM? And TM is not that much relevant, but for SEM, and that's, you will see later on that this is one way of evaluating. We wanted to evaluate the embedding quality. This is quite important because if you have a conductive resin but the embedding is bad, well, you can't do anything. Sectioning properties, because as I was saying, I did that on the microtome, so I did a lot of sectioning. and you will see that the sectioning is definitely not the best thing in this resin. And obviously then going to a volume SEM microscope and doing the charge analysis, and last but not least, the fluorescence preservation. So each time we had a new batch of resin, we've tried to test all of these parameters at once. So basically that was happening like that. I was putting the sample 2x2 into this rosette from the AFS2, you will recognize. And so then I was doing the sectioning. And so that was the first one, that was the second one, a fourth one, and whatever. And I've done a lot of them. And then you can already see that with the same free sub cocktail, the general aspect is quite different. I was trying to have same type of sections, same thickness, trying to fix to 70 nanometer, and same parameters on the TEM. None of these sections were post-stained. So basically I was just taking the sections, going to the electron microscope to remove as many steps as possible so that that would be somewhat comparable. And so I did that over a large amount of samples. And then one of them, and all the samples were high pressure frozen locally. So that basically that's something also that we could always make sure that we had the same parameters. And so the cocktails, we've tested also a few cocktails, varying from 0.05% to 0.1% of uranyl acetate. I always fix myself to keep only uranyl acetate, eventually glutaraldehyde, and 1 to 5% of water. I did not try to put other heavy metal salt because I wanted to narrow down the variability as much as I could. And you will already understand that this is hard to keep as precise as possible. I noticed that the glutaraldehyde somehow increases the contrast to some extent. I don't know exactly why. I have the feeling that the glutaraldehyde tends to squish a bit the membrane, so basically they become denser, and that's what gives me some contrast. I'm not sure if this is just an interpretation or if this is reality. I'm not a chemist again, but somehow glutaraldehyde increases the contrast at the membranes. Then the temperature path was always set to be the same because, again, we want to remove the variability, and we'll come back to that point later on today. And the first thing that we did not want to test was to put osmium tetroxide. I know that many people like to use that because it also increases a lot the contrast in the membrane. It's important in SEM. But the same as for the Lovicryl, the resin polymerizes with the UV. So we did not recommend using osmium tetroxide in this resin, although we cannot prevent someone from doing it, and we'll come back to that point later on. Then the temperature curves, you will be familiar with that. This resembles a lot the Nixon and the Kukulski protocols. So basically starting -80, going up to -40 degrees, or like 5 degrees temperature per hour. And then all of these steps, I think since you will have the video, you can always come back to this protocol in details. And so we've done that over and over and over again. And one day I was at the TEM, and then suddenly I had this kind of image under my eyes. And I was like, okay, I'll have the same imaging parameters as in the HN20 that I imaged a few minutes ago. And the contrast is significantly higher. The image is also a bit darker. So I was kind of, okay, is it because I did not focus the beam where I had some changes and so on? And looking at it carefully, it seemed that the contrast was much higher. And when we looked at the histogram, basically it's more spread. So basically we have a wider range of contrast for the same number of counts. And so that was the first time that we had an idea that somehow the resin was more contrasting with the same conditions. That was, to me, the interpretation that somehow the electrons did not go through the section, and therefore they were dragged away, and I interpreted that as being somewhat conductive. This is obviously an interpretation, but that's you work with what you have as a tool. And one day, a student from Pasteur came to me and said, like, look, Xavier, I know that you're working on this electroconductive resin. We have a big trouble in our lab. Our project is not working. I'm struggling with imaging my samples. Could you give us some of your resin? And I said, look, for the moment, I don't have enough resin because there was only batches of 10 mLs each time I was working with it. So I had to be careful with the amount I had. But I have this block. I don't know. It's good in TEM. Do you want to give it a look? So I gave it to him. being in Pasteur, in Curie. Pasteur is just next door. And he called me back and said, like, look, we have a very great contrast. The images look really impressive compared to what we have usually in our protocol. And so this is the images that you see here, where basically this is exactly what they sent to me and said, look, it's really good to us. I had no expertise in SEM. So myself, I could only trust them when they told me it's good. Because we had that, and because we already had a collaboration very active with Lucy Collinson's group and Chris Petty, I said, okay, I'll take these blocks and I will send them for more extensive work with Chris Petty and Lucy Collinson, and they will look into it and they will give me their feedback with a more quantitative aspect, and not only we've tested it and it gives a good result. So I sent them 4 of the best candidates we had, and they imaged them in parallel, and they just gave me how they felt about it. They did some quantification, they were imaging in a very strict way, but then they just gave me their feedback like, well, this one is nice to do, this one sections well, this one sections not so well, the contrast is good, we have hard time to find the focus, we have hard time to set the astigmatism. So very intuitive way of working. It was definitely not something I would say mathematic driven or physics driven. It was a feeling from biologists doing some work. And they did the test for each of these resin, both with the FIPSEM, on the CCOM, and on the 3-view Zeiss Sigma. So basically, each block was tested these 3 times, and I already had the TEM images before. And they identified that one of the blocks was behaving better, and then they figured by successive steps what were the best imaging parameters. And this is where we started to have like something like a hint. We had a product we could start to try to diffuse. Before going in that part, so then that's when we decided to say, okay, we have a product, we need to upscale it, because having it in my lab is one thing, but as a company we need to be able to diffuse it. And so with our chemist, we decided to make a big batch, and then we had to fine-tune that, because actually the big batches that we could order from the big company to make and synthesize the polymer were not of the same quality as the one we used for the testing. And so basically we had to do this exact same procedure again. And this is something we did together with Jean-Marc Verbavatz and Rémi Leborgne at Institut Jacques Monod. Basically because we were about to launch the product, and then we realized that what we were about to sell was not what we were testing in the lab. So that was quite a stressful period, but we managed to produce on a large scale the exact same product as what we had. And this is when we start to do the next step, is basically trying to combine fluorescence preservation and volume imaging at the same step. Also, of course, at that time, the focal charge compensation was becoming available, and Lucy Collinson had it in her lab. So basically, we tested it, and Chris identified quite logically that actually it's a good combination. It adds up properties, and one is not, I mean, one is improving the other. Obviously, those of you that have the focal charge compensation enjoy it already a lot. But it's a cumulative aspect with the resin. And so this is the kind of images we could obtain from the volume electron microscope. And this one, so you have all the parameters on the presentation here. And again, you will be able to look at them again. These parameters are always given with the user note we send when you are using the resin. But obviously this is subject to evolution, and this is not an absolute estimation. Your microscope might behave differently. That's quite important to keep in mind. So I'm not sure if the video will move smoothly, but I already presented that a few years ago in a meeting, and I know that some of the participants asked me why we had some shadowing and some variation in the thickness. Obviously, this is not the perfect set. This is not the perfect resin that does everything at once perfectly, but it's already giving a significant improvement, and this is what we were happy about. And then if we zoom into this particular region, we see that we have already in the 3-view conditions a very high contrast. We can see that we see the cristae in the mitochondria. We can see the nuclear pore complexes along the nuclear membrane. We can even see some buds near the endosomes. So basically, the resolution we can obtain was already very satisfying, and this was very exciting to us. The same sample, or the same block, was also put into the FIPSEM microscope, and again, we had some very high contrast. So I know that the FIPSEM is giving much higher contrast natively, and this is confirmed here. There's nothing novel in this case, but this gives to us very encouraging results. I hope the video plays well.
Jumps a bit, but I think it works nicely, Xavier. We definitely get the feeling. For a Zoom video, it's no worries. Don't worry.
Thanks. And so, as you can see, in FIPSEM, we could acquire the entire volume. The jumping is coming from the presentation. Obviously, this in this case is not coming from the imaging or from the data set. And as you can see, we can go through an entire cell with a very high contrast and no obvious charging appearing during the imaging. So this is actually the same video, and this is on the right, on the bottom right. This is the volume rendering of the cell. Now, if we look at it in a closer way, that's really jumping. I'm sorry for that. I don't know where it's coming from, but it's definitely from the projection. We can see that we can find some very detailed structures. Here we have the mTOC, which is nicely resolved next to the Golgi. We see that the endosomes are nicely presented, and we can see even the coat at the membrane of the endosomes. Also here we see that very well. So we can obtain a very fine resolution, although we have only 0.05% of uranyl acetate in the cocktail and 0.1% or 0.01% of glyceraldehyde. So basically, although we have what we consider as being very close to no contrasting agent, we already have a very high contrast in the structures. And that was surprising to us. And I remember the first discussion we had with Lucy after she did the imaging, Lucy and Chris, and she was asking me how much UA I placed into the cocktail. And when I said it was 0.05, at first she did not believe me. And then the discussion was like, she thought she misheard me. And then obviously this is the results we obtained. So we were very enthusiastic, and this is the same image without jumping. So as you can see, we see the nuclear pore complexes, we see the coat under the endocytic vesicles, the coat at the endosomes, the Golgi and the COP1 coating. So all of this is very sharp, and this was to us encouraging. Now, as I mentioned, when we put the uranyl acetate, whatever volume we put, this is a trade-off with the fluorescence. And already at 0.05% of uranyl acetate, we get some decrease in the fluorescence. That's something we noticed. But what is very interesting here is that in that case, I did the free substitution without any fixatives at all. And then here, this is the image of the sample after sectioning in TEM. And as you can see, the contrast is inexistent. We see barely anything. And then this is with post-staining. So the post-staining brings up a bit of contrast, but in no way it's comparable to what we got in the free sub cocktail having 0.05% of uranyl acetate. So I don't know how this works. I have no clue, but one thing is sure is that having the UA directly into the cocktail during the free sub have much better impact than the post-staining. And having no contrasting agent in the resin makes it completely it makes no contrast, and somehow it's charging the same way under the electron beam in SEM. So what we have to keep in mind is that the resin itself is not conductive, but in combination with a heavy metal salt, it starts to have conductive behavior. And one of the interpretations we have is that the resin behaves like a semiconductor. Semiconductors are molecules that are insulators. And as soon as you change the lattice and as soon as you change their native state, they become conductive. That's the behavior of a semiconductor. And that's really what it's reminiscent of looking at this behavior of the resin. Now, one key thing was about the fine quality we could get. How does it preserve the ultrastructure? How does it behave in the microtome? So this is a wide example. This one are melanocytic cell lines, so MNT1 cells. Sorry. And this is the results here. So there are very dark patterns, but we see that we have a very homogeneous contrast and it's nicely contrasted. Here, this is a C. elegans worm that was also contrasted. All of this is the cocktail we used. And these are yeast. And we can see that we have already high contrast. And we can see very sharply the membranes and even the bilayers of the membranes quite clearly. And this is visible in all type of samples. So the ultrastructure preservation looked good to me, but obviously the sectioning was a big deal. And so what we noticed is that the embedding is not ideal. If you have some fragility regions, the sections will break up, and this makes a lot of holes. So basically the resin is not ideal for TEM and microtomy sectioning. This is redesigned for volume electron microscopy, where the block actually remains solid and then you shave it on the surface. What we also noticed is that sometimes, and it happened to us once, basically it just chopped off an entire piece inside the block. And so that's what happened once with the nucleus, where we had the entire nucleus chopped off from the block. So the embedding properties of the resin is not as great as HM20, for example, or as EPON. But it gives us some good results for the applications we're looking into.
Xavier,
so,
can I just ask a question?
Yes, please.
Sorry to jump in. Did you ever try an oscillating knife on this resin?
So not yet, because I don't have it, and I should ask Helmut if he could share with me for a few days.
I mean, we have one at the Crick that it's not ours, but we could probably make use of it. So I mean, obviously the sealed block face, the three of you has an oscillating knife, but to do it outside, then we might be able to do that. Yeah.
That could be great. Yeah. So well, thank you, Matt, for this suggestion. I did not try it again. I've done this work that was a side project for me. I was working mostly on the high pressure freezer that you see behind me on the presentation. And I wanted to have this resin extra. So I must say that that was not 100% full-time job. But this is very interesting, obviously. And so what we did is this kind of work. And as you can see here, this is reminiscent of what you just saw before. When we have no contrasting agent, no glutaraldehyde, then in TEM, the contrast is close to non-existing. But as soon as you put traces, and I'm talking about 0.01% of UA, so we even decrease the amount of UA, we start to have a high contrast even in CCOM or in TEM. So this is kind of coherent with the semi-conductive behavior of the resin, or what we interpret as being a semiconductor behavior. And then at some point, when we increased the amount of UA, we went up to 0.1% of UA. It's kind of reaching a plateau in terms of contrast and also in the behavior in the SEM. 0.1% is not much better in the SEM than 0.05%. Again, this is very empirical observations, and I do not quantify that. I don't know how to quantify it, to be completely honest, but that would be most likely interesting on the long term. And the glutaraldehyde to some extent increases also the contrast. So this was to compare with the HM20. Again, this work was always done in a parallel way so that we could see the improvements if there was some. And so if you put the two images next to one another, here in that case, this is in absence of any contrasting agent. As you can see here, no glutaraldehyde, 5% of water. And in HM20 versus R221, we see that we have a bit more, and this was done in a CCOM, we have a bit more of contrast, and the images are slightly sharper. It's easier to get some focus, to get a proper focus is easier. And as soon as we put a bit of uranyl acetate, the contrast becomes significantly sharper. So that's another way of estimating the improvement of the resin over the HM20. Again, this is not quantitative. We are working into quantification of all of this. This is one of the work we've tried to do with Chris, but the COVID came into play. So we are starting back this work now. But as you can see, we already have some incentives that it's getting, we have a more contrasting resin, and we call it conductive. Maybe this is an abusive term, but that's the behavior it gives. And so obviously all this work had to be integrated into one single experiment, and these images are more for the pleasure. So basically what we did is high pressure freezing C. elegans worms that were expressing both GFP and RFP, embedding them into the usual cocktail, and then doing in-resin fluorescence microscopy. What we observed here is that using a confocal SP8 from Leica, we could get very sharp images. And what is interesting is that in those data set, the laser power was brought up to 40%. So for those of you that are familiar with confocal microscopy, we rarely go above 5%, and 5% is really a maximum that people tend to use. Normally it's 0.04%, 0.4% of the laser power. Here we're at 40%. So it's significantly more, 100 times more. And not only it gave very nice results, but we did not observe any bleaching, and it did not alter the structures underneath afterwards. So this block was imaged at the Curie Institute, and then I sent it to Chris so that it could do the volume electron microscopy. And so that he could get familiar with the block, he went back to an epifluorescence microscope, and he could image the same worm and look at it again. And he was not looking for the fluorescence. It was not bleached, and we were using, again, a huge amount of laser power. So and so then what he did was to acquire 3 view data sets at these different locations and a FIPSEM at the head of the worm. And so basically, this is the data we could obtain. Here has been segmented out. This one is the volume, and this is the FIPSEM. And so what we did afterwards was to combine these images together in the computer. So for that, we use ECCLAM. For those of you that know me, it's a software that we co-developed with Perrine. And though basically what we did was to place the structure directly into the volume and then combine the images. So as you can see, the matching is quite good, and this is expected in a way, simply because we're looking at the same volume, both in light microscopy and in electron microscopy. And so basically, since we're always looking at the block and not at the sections, we're looking at unaltered structures. So basically, the matching is ideal, if not to say optimal. So this is a side effect, but this is a quite interesting one. So that's the way we did it. That's the visualization, and all of this combining was done with ECCLAM. So I'll let you appreciate the final images. And again, this was done with the 0.05% of uranyl acetate and water in the free-sub cocktail. So it's very mild amount of UA, which is also one important point, because UA is becoming challenging everywhere. And one of the steps we're about to start now is to test alternatives to UA to see whether we could use something else. 4 weeks ago, Andrea mentioned ULS and UAR. We're also working, we're also looking into lanthanide salt, and we'll try to see whether it has the same quality or not. And so the last thing, because it has been asked several times, and this is one of the point which I think is important, is how the protocol we've been recommending so far is subject to evolution and what could be improved or not. So what we've seen is that the free sub cocktail from 0.01% starts to be functional, up to 0.1%. The glutaraldehyde, as I mentioned before, gives some higher contrast. What is the mechanism behind? I don't know exactly, because it's definitely not a contrasting agent. The importance of keeping water into the free sub cocktail is essential, and dry acetone is to be kind of always strict that on the volume of water we have in. As I mentioned at the beginning, the osmium tetroxide is not recommended. However, 2 weeks ago during the ZEISS meeting, I discussed with Paul Verkade, who told me that he used osmium tetroxide in the R221 resin, and it polymerized well, and he was happy with it, and he's looking into the results right now. So this is one thing that is about to be more widely known. Also, immunogold on sections has been tried once, not successfully, which was not the point of developing this resin, but why not trying it? For the moment, I don't have anybody came back to me saying like, oh, I have a protocol that works. I only had one trial telling me, well, it didn't work. Again, that was not my main focus. Another point that was raised by Paolo Ronchi from the MBL during this ZEISS meeting was the slope at which the temperature should be raised during the free sub cocktail. And he said that in their hands, now instead of raising up the temperature from -70 to -40 at 5 degrees per hour, they're going 3 degrees per hour, and this increases the contrast significantly. So this is something I will try myself and try to see how much it influences the quality. But obviously, this remark is important, and I will integrate that in my work, in my forthcoming work. Another thing which is annoying to all of you is the fact that the resin is not that much fluid at -30 degrees. It's quite viscous. So that's quite annoying. And so what I did was to try to embed the stuff at 0 degrees Celsius. So basically the 100%, which is the most viscous part, at 0 degrees Celsius, and it works fine. And the embedding is quite good. So I'm also looking into raising the temperature more progressively along with the embedding step with the resin, up to reaching 0 degrees Celsius with 100% resin, so that basically the embedding will be better, infiltration would be easier, and so the handling of the resin on its own will be as good as Lobicryl, hoping that we will preserve the ultrastructure and having a better embedding. So this is something which is also in the pipeline. This is not yet completely fluid, and I need to work on the practical aspect of this, but this is one thing I would recommend if you want to give it a try. I know that at 0 degrees Celsius, 100% works fine, and the embedding is okay. So that's something to look into. So to finish with this, obviously this work was not done on my own. You will recognize obviously the company, which has been supporting and financing all this work. We have some industrial partners. We've worked a lot with ZEISS on the integration of other technologies, the microscope you see behind me integrated with high pressure freezer. But I must emphasize the work that was done together with Lucy and Chris from the CRIC that could not have done. I mean, I could not expect better partners in this work. Jean-Marc Verbavatz and Rémi Leborgne at Institut Jacques Monod, who saved our lives when we wanted to launch the product, and this is something important. We have some collaboration with Nico Somodijk and Anat Akiva on the correlative aspect of work. Back then, I was doing this work at the Institut Curie under the supervision of Grassa Raposo, and together with Jean Salamero. I mentioned Perrine Pogilotto for the ECCLEM software. This is something different, but this is always related, correlative microscopy. And since this September, we in the Kremlin-Bicêtre in the south of Paris, And we are now establishing our own lab. So basically we will be able to do novel work on this resin and other applications. This is the Dropbox link that Erin just mentioned in the discussion channel. Feel free to copy paste from the discussion channel. It will be easier than just repeating it from the screen. The Dropbox will be available and remain available for coming weeks. But again, there is nothing that you could not find elsewhere. I think it's a important work that led to this development. So I wanted you to have a chance to look at them. And with this, if you have any questions, I'm very happy to discuss them.
Thanks, Xavier. That was great. Does anyone have any questions? You are welcome to unmute, to raise your hand, to, I don't know, jump up and down. Andreas has a question. I already see a paw up. Andreas, take it away.
Yes, Xavier, thanks a lot. So I have a question. So you say that if you have your resin and you make a section without any contrasting agents during free substitution and then try to do post staining, you cannot get more contrast, right? So that means that all the optional ionic interaction bonding signs are already taken kind of when the surface is exposed. Because you know, if you look at the Matzko and Müller papers, where we did some experiments by just using epoxy as a fixing agent in the free substitution, no heavy metals at all. And then on this section, you can, with the post staining, you get very good contrast. So this is very astonishing. You have a clue what is going on there?
No. One of the feeling I have, and I would refer to Erin because this is something we tested during my PhD, is that basically we noticed that when you do the post staining, the stain is not going all the way down into the section, and because it's not going all the way down, you have in the end a staining of only the few top nanometers, and therefore you have a less efficient contrasting. That's the observation we did on tomography. It was already almost 10 years ago now. But this is the same feeling that I have. I did not do tomography on these sections because I considered that as a side effect.
Yeah, so as far as I know, the post staining never really goes deep into the section. I think there are very old papers out. I think Heinz gave me once these paper. So they did even cross-sectioning, re-embedding and cross-sectioning of the section to see how deep the metal or the post-staining really penetrates inside the section.
Xavier, what you experienced there with the methacrylate resins is similar to what I've found. That if there's nothing there to start with, then no amount of kind of post-staining will bring out anything.
Yeah, I will just say we had when Xavier and I were fighting with this, it was really the UA, and it was really on the thick sections for the F30. The thinner sections were okay, but we got much better results if we just dropped UA completely from the post staining and just used lead. So ultimately, we tried to put things in the cocktail for the free sub. Xavier, I have a bunch of other questions if no one else does, because you know me, I always have questions. You answered some of them as we went. The viscosity was great because I was curious about that. So really, it's a bit of a struggle, but you're working on that, which is nice to know. I wondered, because you know us, you and I lived in the world of tomography for so long. I wondered, so you haven't done electron tomography of this because of the section challenges, although Matt's idea of the oscillating knife is a nice one. I wondered if you've done any beam stability tests to compare thinning or responsivity in the beam or anything like this. I mean, these are mean questions because this all takes a truckload of time and you've been busy just developing it, but it would be interesting to know how it responds in the electron beam.
So indeed, I have not tried that. What you will notice if you do the thin sections is that basically if you expose the sections to intense focus for a short while, it will extremely quickly thin down and it will extremely quickly become much more contrasted. So basically it will look up very dark and very homogeneous and not so good when you look at it from low mag. You zoom in, you zoom out, and then suddenly it becomes extremely clear. So it goes along this way, but I have not quantified anything. I just observed that.
Okay, because the I guess beam stability. I mean, I'm not an expert in resins. You will know much more than I do, but I think, I mean, the nice resins for the volume SCM. I think some of it has to do with the beam stability, right? Or the consistency in fib milling and things like this. These ultimately would be important properties too, I would guess. So all in the development process. Going through, switching topic a little bit, going through, I noticed you've done cells and C. elegans. Have you tried any other models? I mean, I'm thinking plants or yeasts. I mean, those two were
Yeast.
monsters to infiltrate sometimes, right?
So yeast have done it, and it infiltrates not ideally.
But
One
yeast
of the
is evil for everything, so that's not your resin.
yeast, actually, one observation, but it's not related to the resin, but it's kind of related to high pressure freezing, is actually if you have very challenging samples, slightly bad freezing will improve the infiltration. Yeah. Because you will start to crack open ice needles through your membranes, and then infiltration will get better. So in a way, it's kind of, and that's something completely unrelated, but this is related to the machine behind me, is that we're working on adjusting high pressure freezing parameters to actually, in some tricky samples, make the freezing slightly worse to improve the infiltration. That's something we have in the pipeline, but that's unrelated.
But it makes sense. It all comes down. I mean, in EM, we have to admit we have artifacts everywhere. We'd like to think we don't, but it's controlling our artifacts, I think, is our key, right? So at least this is my opinion. Okay, so I have more on the list because I always have questions. You talked about 1% to 5% water. Have you tried no water? Because some people would also say that your water is another, I mean, I'm saying yours, I don't mean this as you personally, but addition of water to free subs is also the introduction of potentially another artifact. So did you try 0% water?
No, because if you read the paper I mentioned from 2007 from Walter and Buzer, is that basically what they noticed is that when you open the bottle of dry acetone, it captures the water in the atmosphere, and it's no longer dry. So basically, I did not go into the struggle of opening it under gas and doing all of this to make sure it's completely dry. Because I didn't do that, I will always have some water, and therefore I decided to add in a fixed amount. Obviously, this adds some variability because the humidity that will enter the acetone on a rainy day might be different. I decided not to go into that work. It was published. The results were obvious. I just took that for granted.
You just went for it. You obviously haven't done EM in Portugal, because we look at things and it's humid here. It's always a fight we have. If anyone else has other comments, jump in. I'm just going through my little thought list here that I had. So no water. This is also one that, as a head of a lab, worries me always. What is the toxicity and the work requirements with this resin? Because is it evil? I mean, HM20, you don't want to breathe it, you don't want to touch it, you don't want it anywhere near you. So what about yours?
So I have a good and a bad news about that. The bad news is that, exactly like HM20, it's a methacrylate resin. And so basically, you don't want to get in touch with it. The very good news is that it's an evolution. It's a different way of doing the resin, and the resin is way heavier, is way longer polymers. That explains the viscosity at low temperatures, because the resin, being heavier and longer, becomes more viscous. It interacts in a different, more sluggish way, but it's also less volatile. So this is related to the various parameters, but basically, if you consider the HM20 would be X long, I would say our resin is 20, 30 times X longer.
Mm-hmm. So it's not as much of a aerosol, if I'm understanding correct. It's not as toxic in this way. Matt's
you
unmuted.
Don't smell it.
Yeah,
you
you
barely
don't smell it.
I was going to say, is it as stinky as the? And obviously not.
It's barely as stinky. I mean, obviously, if you're just working in the AFS and you're doing all the exchanges right above, you will get it, but it's not like the HM20 where you enter the room and you smell someone is working with it. It's definitely not that bad. I would recommend anyway, it's a methacrylate, so I would recommend in any case to take all the security considerations, but you won't worry as much.
This is a horrible question, and I don't know how to do this without putting some poor person to suffer, but I've heard, thankfully I don't have this, some people have methacrylate allergies after dealing with these resins, and they can't even touch a polymerized block anymore. Do you know, have you victimized anyone to see if they can touch your resin?
No one came back to me saying like, oh, look, I'm going to clinical test because of you. I'm knocking on wood for that. But obviously it's a methacrylate resin. So I mean, we recommend using gloves, lab coat, goggles, and if you work, it's under the fume hood. I mean, all these recommendations that you would do for HM20 applies to us. It's a methacrylate resin. Methacrylate is a nasty product.
But even when polymerized?
I've not tried it.
Because some people I know can't handle HM20 blocks even when polymerized because they get skin allergies. So this, I guess it would be interesting to know if there's anyone in this group who has this horrible side effect. It might be interesting just to see what this one's like. But thankfully, I think we've all used gloves enough that none of us have this nowadays, which is a good thing. Matt, you're unmuted again.
I'm just chipping in again. Personally, I use gloves when I'm handling blocks anyway, because I don't want to get my greasy fingers on it and interfere with the sectioning.
Yeah, absolutely. Okay, so I have one last question if no one else has any other thoughts. And this is also a naive question for me because I am far, far, far from a volume EM person, but I've seen these lovely protocols where people are doing different etching techniques on their resin in light microscopy so that then they can try and relocate a bit more easily in the sectioning or the clem techniques. Have you tried anything like this, Xavier, to see how it responds to etching?
No.
No? Okay.
No, I don't have the equipment here on a routine base, so I did not try it. But I assume that if you have a pulsed laser, it should work the same. I mean, it's just a burning function where you heat locally the thing, so it should work. But I have not tried, and so I cannot give you any hint of how to handle this.
Well, I don't blame you for having not tried, because I honestly, looking at all the evaluations you've done, I can only imagine this has been an enormous amount of work. So if you, what is your wish? I mean, if you can answer this, because I don't want to take away any company secrets ongoing, but what is your wish for where you want to go, or is your goal at the moment to get something great for volume EM, and then from there you see where the winds take you, probably?
Well, that's obviously the challenge of a company is to make sure that your company is still alive for the next coming years. So anything we do is trying to make something that will suit the customers, and you are a large bunch of them. So the idea is to produce that. I might not go into a next round of improvement of the resin soon, because the amount of work is tremendous. The money that it represents is you scale it up. So we have a resin that works for now. If the community is satisfied with that, great. If the community is asking for more, then we will need first to make sure that the community buys the first one. So it's kind of, if you have more purchase, then you can develop more. And I don't handle that. I'm not the one in charge.
You are a brave man, Xavier, because the community will always ask for more. You should know that by now.
Yes, but you cannot ask if you don't support.
That's true. Andreas, you have your hand up. We'll give you the last question.
Yeah, thanks. Sorry, I was just switching in very late. So, but I have kind of a boring question maybe too, but maybe the whole community could answer anyhow, because so you were already addressing this regarding methacrylates and so, and how dangerous they are, and we all know that. I'm actually just thought about regular handling of these polymerized blocks and all the trimming and all these kind of things, especially actually trimming. So what you guys are taking care of these? I mean, there's tons of debris and all that kind of things floating around. Is there anybody who has some really clever solution for this?
I don't know if it's a solution, but what we did when I designed our lab, we had the option of having very gentle compressed air. So now what we do is all around the ultramicrotome stations, we have essentially a little hose that's of compressed air. Of course, you don't blow it into the microtome. This has to be really careful. You make sure you blow the crap or the debris away from the microtome. This is not a thing though for a health and safety standpoint. This is more just a clean workstation. So if your question is in the line, Andreas, of what do we do from a health and safety standpoint, I don't know. I don't have an answer.
Because so we have connected. There's like a vacuum dryer on the trimming machine and so on. So we do all the trimming on this trimmer and try to suck off most of it. But still, I'm kind of not really. Yeah, I mean, we're at a hospital, and I think if I'm not 100% convinced about how well this works or not. Of course, nobody in our lab had some problems, but if I think about it, I mean, I have a dust bin in the vacuum filled with methacrylate debris, and is that cool?
I mean, maybe we need to put this in the lab waste, not in the like office waste. Or...
Yeah.
Michael, nice to see you, first of all, and secondly, what thoughts?
Yeah, just I wanted to answer the question of Andreas. So we use a particular vacuum cleaner, which has a filter inbuilt. It's a professional vacuum cleaner from Kercher, and it's also for biosafety level 2 lab usable. So as you know, we have biosafety level 2 labs and more, and we use them in our biosafety level 2 lab for cleaning everything there, including the debris of the trimming. And this is quite efficient, and you can close the box without any contact, and it's in a particular enclosed in a particular sac and filtered, and this helps a lot and is quite safe. So it's not very expensive. So therefore,
yeah, but sounds good, interesting.
Yeah.
Kercher, you said, huh?
Yeah, it's a Kercher. It's from the professional line of Kercher. They offer a lot of and even larger systems if you like to have them.
Can you share which type it is from Kercher?
Yeah, I can do this. So I will have a look and put it. So I send it to Erin and she will transmit it.
I can disseminate if you'd like.
Yeah, disseminate is right.
Paolo, any thoughts? Uh-oh. Shit.
We have some resin which is about 3 years old. It's in the chemical cabinet in a dark and dry environment, sealed with parafilm, and this is still working fine.
Okay.
So I can tell you that for 3 years it's fine. I'm not sure about 4 or 5 years, but 3 years is fine.
Yeah, perfect. Thank you.
I'm back. Sorry, unstable Wi-Fi and multiple Zoom meetings happening from my house at the same time. It's a typical strategy in this world, right? Any last thoughts? Angie, did you just want to ask for the link, or was there anything else that you wanted to jump in?
Actually, for avoiding this dust during the trimming, sometimes I just wear a mask. These FFP2 masks will do.
It's nice.
We see Paolo is wearing one, so.
Yeah, exactly. Our new worlds kind of combine, don't they?
Yeah.
Well, I think this was great, Xavier. Thank you very, very much for this. Everyone, please take note of that Dropbox link just so we don't lose it. I downloaded it and checked. I have a copy. So if you have a panic and have trouble downloading, you can always ask me and I can share again. And I thank you all for joining us today. In 2 weeks, we'll have a great talk from Andreas Müller about their new paper. So I'm really looking forward to this as well. This, I think, will be superb. Thank you very much, everyone.